Hello everyone, my name is Hölzemann, and today I'm going to present our paper digging deeper towards a better understanding of transfer learning for human activity recognition. Datasets of human activity data from wearable sensors contain different activities from specific domains, like for example sports or activities of daily living. Deep learning classifiers achieve different classification results, depending on the dataset attributes as well as the used network architecture. Since we don't want to train our neural networks for every dataset from scratch, it should be easily doable to reuse already trained models with techniques like transfer learning. Or isn't it? We wanted to have an answer to this question. To execute our experiments, we choose the PalmUp2 and the Skoda mini checkpoint dataset. Both datasets are known in the research community for many years and it is already proven that they are suitable for deep learning applications. These two datasets share important attributes, like for example a nearly same sampling frequency, similar sensors, and similar recording locations on the body. However, they are fundamentally different regarding the activity classes. The PalmUp2 dataset contains activities of daily living, whereas the Skoda mini checkpoint dataset contains activities from the assembly line of a car manufacturing process. After corresponding with the outputs of the datasets, we realized that they are recorded with different sensor orientations. We therefore computed every possible permutation and rotation of the axis to be able to test if the classification results increases if we match the sensor alignments. We trained two different baseline models, one with the wrist-worn accelerometer of PalmUp2 and one with the right-hand data of the Skoda dataset. We then transferred these models using weight transfer and 4 different methods. For every transfer, we replaced the classification layer with a new untrained one. The 4 methods are: first, freeze all layers except the classification layer. Second, freeze all convolutional blocks but leave the rest trainable. Third, similar to method 2 but reinitialize the LSTM layers with the default initialization algorithm. Fourth, leave all layers trainable. For more details, please have a look in the paper. We got a lot of results, so let me show you the most interesting ones regarding the training of one scores. When we leave all layers frozen, the results drop much lower than the baseline results. When we leave the convolutional blocks frozen and fine-tune the LSTM layers, the classification results improve significantly. However, they get a few % better if we reinitialize the LSTM weights with the default initialization algorithm. Experiment 3 and 6, which are intra-dataset transfers from one sensor placement to another, are very interesting. They show that even after artificially matching the sensor orientation by permuting and inverting the sensor axis, we are not able to nearly reach baseline F1 scores. It is surprising that although the modalities of both datasets are largely identical, a transfer between them is always accompanied by strong performance losses if we do not fine-tune big parts of our network. In future publications, the spotlight should be put on how and why transfer learning works for specific deep learning architectures or datasets, and why not for other ones. Therefore, it is important that we take this work as a starting point from where we need to go much deeper. Thank you for your attention.